3, 8, 23.
You said calculator, you can't on the ground.
So,
You said you need one.
Oh,
no, you don't need one today. I'm like, if you ever do need a calculator,
Oh, okay.
that's what I was thinking.
Yeah.
I was like, what?
Oh, no, I thought you.
like if I'm doing math problems in class and I tell you I'll go grab a calculator, you'll grab 11, you'll grab 12.
Oh, yeah.
Or if I say up in Chromebook, we're doing an online Kahoot quiz or something.
11, 12.
All right, beakers. Y'all know what a beaker is? So beakers are used for holding various chemicals. They are not meant for measuring things precisely. So if you don't need exactly 200 milliliters, if it can get away with minus or plus 10 or 20 milliliters, they're a great tool. We'll mostly be using beakers as our measuring because most of everything we do, don't really care how much water. We are not, as long as the water is in excess. It doesn't have to be precise, but if we do need it to be precise, we use something called a graduated cylinder. It's used to precisely measure the volume of liquids or run experiments. Read from the meniscus at eye level. Plastic ring is always on top if applicable. Do y'all know what the meniscus is?
It's like the little dip in the liquid. It's like the lowest point, like that little dip right there.
So there are two meniscus. There is either where the liquid will hug the sides and form like a dome parabola. So yeah, exactly, because surface tension. Here this is hydrophobic. This is hydroscopic, where it's going to rise up. So regardless of which way it is, you will measure from the middle of the bubble.
Yeah.
And you want your eye to be looking this way. You get your eye horizontal or at eye level with it, and then you look through it like that. Erlenmeyer flask, it's kind of like a beaker, but it's more helpful in stirring and mixing. So if you need to make some salt water, and you're not too concerned with how precise you are going to be, like approximately 200 milliliters with like 10 grams of salt, it's very helpful in stirring it up. Because of the shape, whenever you stir it, the water is going to hit, when it goes vertical, it's going to hit the slope sides and bounce back down. If you tried doing it in a beaker, you could potentially spill it. So it's very good for mixing the swirling. A Florence flask is used to boil liquids. It also can be used to collect gases if applicable. Reason why Florence flask is used for boiling is because of the shape of the bottom provides a lot of surface area, which means you can heat up a lot of the liquid, and also due to the shape on the upper portion, whenever it starts to boil, you're not supposed to fill these up like beyond halfway, like only like I can't mouse over, but you're only supposed to like the sphere. You're not supposed to go over halfway. Because if it starts boiling and the bubbles reach the neck of the flask, then you're in trouble, as it can overshoot and quickly extend upward. But the roundness of it tends to pop the bubbles and make it fall back down. Volumetric flask is very precise for making very precise standard solutions. This is useful if I need to make like a certain concentration of sulfuric acid, in which case you usually will make like 100 milliliters, 200 milliliters at once. in which case the difference between a graduated cylinder and a volumetric flask is the flask is only good for exactly one volume. It's only meant, you can see that line on it, it's only meant for exactly one volume. And also it provides a much greater volume than a graduated cylinder. Reagent bottles, after making some solutions, a lot of times you want to save them or let them run overnight, and some of them take a long time for the reaction to actually occur. Unless you're making giant big quantities of it, you usually put it in a small little bottle. Rubber stoppers are used to close flask and test tubes. A lot of them have holes in it to allow inserting glass tubing through it, or to insert thermometers into the hole to measure the temperature while it's going on. Test tube and rack is used to hold chemicals tubes while experimenting. It's not meant for measuring precisely, and also so some gases are denser than air, which means if you if you put some chemicals into a test tube and it starts producing this gas, that gas won't leave out of the top and enter the room. It'll sit there and collect. It'll become highly concentrated at the end of the test tube, which means if you get your face anywhere near it and breathe, when you breathe in air, you'll breathe a highly concentrated gas into your lungs, which, based on concentration, could be very bad. That's the reason why you waft, it doesn't get much out of the test tube, because it's heavier than air. Always aim it away from your faces. Never put any body part above the tubes, because a lot of chemicals like to spontaneously react violently, and because it's such a narrow test tube, it can spray out. Distillation flask used to separate liquids based on boiling point. The gas will build up top and then it'll run down the side, and some of the gas will make it through that neck area pointing downward, and you can collect the gas and let it condense on a container. A barrette and barrette clamp is used for precisely measuring liquids as they're being dispensed. And then the barrette clamp is allowed to hold the barrette to a ring stand. Ring stand and ring clamp. Base pole setup for experimenting, holds glassware in place for heating or evaporating. You can also hook up temperatures to it, and so you can put your glassware down below and have a rod or a thermometer attached to the ring stand to hold above. Test tube brushes for cleaning. You must clean tubes before and after use. So some chemicals are very sensitive to the presence of extra chemicals. So if your test tubes, beakers, and stuff aren't fully clean or have been sitting there, chances are that you could introduce that unwanted chemical to the reaction. A test tube holder is used for carrying and holding hot test tubes. Again, you can't tell if it's hot by looking at it. So once it's heated, you'll need to use a test tube holder or some form of tongs. A thermometer for measuring temperature. We will be using the metric in this class, so no Fahrenheit, only Celsius or Kelvin. Hot plate, used to heat substances. Bunsen burner, used to heat substances very quickly or reach very high temperatures. Do not use next to any flammable substances such as acetone, alcohol, or anything like that. Rubber tubing, used for a variety of things, connecting Bunsen burners to gas stem, or connecting glass tubing together. When heating something up, you would want to use a wire mesh or wire gauze. Whenever you put glass over a direct flame, the flame is going to heat up a specific spot that you don't want. It'll get that one spot really hot. You might even melt the glass or cause it to break and crack. By putting a mesh over it, it causes the flame to dissipate over the entire mesh, which enables it to heat up the glass more evenly. Clay triangle used to hold a crucible in place on a ring stand also helps absorb and spread the heat of the flame so that it's not concentrating on one spot. Crucible and cover are used for heating substances that can withstand high direct heat. Some crucibles you can put into a furnace and melt steel in them, and the crucible doesn't get damaged at all. They can withstand very, very high temperatures. Crucible tongs are used to carry the crucible. Beaker tongs are used to carry beakers. Mortar and pestle used to grind up substances into powder. A lot of chemicals, because Texas is so humid, they soak in moisture and harden up. So often you'll have to grind them up to make more powdery. Scupula is used to scoop up chemical powders. Sometimes you need to break it up and to extract it out of a small test tube. It's basically a V-shaped piece of metal. Or don't have any handles, it's just the metal. Stirring rods are used to stir glass. Most chemicals don't like to stick to glass. When you stir it and pull it out, only the liquid will stay attached to it. The chemical and powder usually don't cling to it except via static electricity. Can be used to kind of crush to basically stir is primary purpose. Striker used to ignite gas from a Bunsen burner. As you squeeze the handles together, it causes a spark. It has a finite number of use. It has a flint rod, and you're scraping the flint off, so don't just constantly strike it. Watch glass used to show chemical reactions. With the shape of it, it allows the liquid to spread out and for you to easily see it. You also can put a watch glass. One of the primary things is if you're evaporating this, you're evaporating or doing something, you can put a watch glass over it so you can see through the watch glass and observe the liquid evaporating under it or something going on. Centrifuges are used to separate suspensions, solids from liquids. Meter stick used to precisely measure length. We'll be using the metric system, so know your meter. A meter is 10 decameters, 100 centimeters, or 1,000 millimeters. Funnel, if you need to safely transfer substances from one container to another, use a funnel so you don't spill it everywhere. Dropper and bottle, used to measure out small amounts of liquids for experiments. So you can roughly estimate a drop. You need to add a small amount. Wash bottle usually contains deionized water. So all the water you've ever encountered more than likely has been normal water and not pure. It has lime, it has salt, it has other chemicals that have been dissolved into it. To very small, even though it's very small, it has free-flowing ions. Deionized water is actually pure water with nothing else in it. Something you shouldn't ever drink. If y'all know osmosis, pure water. If you take pure water and a cell has salts in it, the salts and the pure water want to equalize the concentration, so the salts will leave your pure water would rush in to dilute the cell, causing your cells to swell up and explode. Goggles and aprons, need to wear it in the lab. This is only for glassware, heat, or chemicals. If we're not using any of them, then it's alright to, for my policy is you don't have to wear them if we're not dealing with any of those three. And inoculating our flame loop, we won't be doing anything biological. So they're usually done for demonstrating the spectra of chemicals when they burn over a fire. You put a small sample of it on the end of the flame loop and put it over a Bunsen burner, and it'll change colors as that chemical's burned away. Digital balance, used to accurately measure mass, only up to 200 grams in our lab. So if you need anything larger and to precisely measure, you'd have to use a triple beam balance. Triple beam balance measures the mass of an object. You need to make sure that the balance is properly calibrated. Double pan balance if you need to compare two masses, some equal, for example. Centigram balance, used to precisely measure the mass of a substance, more precise than a triple beam balance, so you need to get ultra precise. Pipette, pump, and bulb, used to precisely measure the volume of liquids in small amounts. A Burrell pipette is probably going to be one of the more common things because they're disposable. You have a lot of them that are granulated and can measure very small amounts of chemicals and then be thrown away. Capillary tubes, used to collect liquid through the process of capillary action. Alright, looking at material safety data sheets. So material safety data sheets are supplied whenever you buy chemicals, particularly dangerous chemicals, or any lab or industrial chemicals. They must be accessible to anyone in a workplace, must be current, must be made available to anyone that's participating in the event of exposure, and can be requested. So looking at your handout, that'd be the second and third page, is an example data sheet for acetone. Acetone is used in fingernail remover, polish remover, and also a lot of cleaning supplies. It's really good at cleaning things up and dissolving. Whiteboard cleaner usually will contain acetone. So, you know how spot terms and know what they mean. Flammable. Any substance easily ignited and quick burning, including liquids with a flash point below 95 degrees Fahrenheit. Any substance alone or via chemical reaction able to cause harm, produce injury to the body through absorption, ingestion, inhalation, or injection. Caustic, any substance able to burn, damage, or destroy organic tissue by chemical reaction. Also corrosive is another word for caustic. Flash point is the lowest temperature at which a liquid produces enough vapor to ignite. So, basically anything that's below like 95 degrees, basically you get a lighter next to it, and chances are it will catch on fire instantly. Density. So we're all exposed to dangerous chemicals. That's all right. Our bodies can tolerate some level of chemical. So there's a lot of definitions about how much you can be exposed. For example, my friend installs X-rays for dentists. Every week he's in a new state, a new dentist installing a brand new X-ray for that company. He is exposed to lots of radiation. All right, we're exposed to radiation from our TVs or cell phones, and going on the sun is probably the primary radiation you receive. The radiation causes skin cancer, but you don't immediately burst out in skin cancer every time you walk outside. Reason why is because the more you receive, the more chances it is to harm you. There's acceptable risk. You shouldn't lock yourself inside with no electricity for the rest of your life because you're afraid of a small amount of danger. Going outside is perfectly fine, but if you were to stay outside and never seek shelter, you will end up damaging your skin for having very long-term exposed to it. So PEL stands for Permissible Exposure Limit. It is the standard recognized by the industry as the maximum amount of concentration of a chemical that a worker may be exposed to, what they regard as being safe. TLV is threshold limit value, is the recommended limit for chemical substance exposures, similar to PEL, but most often more restricted. TWA is an 8-hour time-weighted average. So my friend who works on X-rays and gets exposed to X-rays all the time, he has to wear a little badge that records how much radiation he receives, and it's not based on one single time. It's based on either 2 weeks or monthly. They look at it and be like, "Oh, you were exposed too much this week or last month. You need to stop working and rest." Because it's more of some things are only affect you if you're exposed to them for long periods of time, not short periods of time. So for TWA, you can be exposed to that level without harmful effects during the 8 hours. Short term, there is also some chemicals like acetone you don't want to keep on your skin for a long time, so they have a short term exposure limit. No more than so much within a 15-minute period. And then there's a ceiling, it's the maximum concentration that never should be exceeded. I think on y'all's last page, I don't know why this is blurry, there's a write-in. It's up to you, these are notes, you're keeping them. But red is fire hazard. It's it's measured on flame point. These are technically measured on multiple things. Fire hazard can be classified based on flash point, how easy it is to ignite. Things like there are some things that will catch on fire easily if you put them in an oven, but at room temperature it's really hard to set them off. You can't put a lighter to it and light it, but if you stick it in the oven, it'll immediately catch on fire in there once it gets to above 200 degrees. The left one is blue and is a health hazard, how toxic it is, for example. So water would be a 0. Something like potassium cyanide would be a 4. The right one is reaction or instability. It depends on what it's measuring. The chemical is 2 things. Usually it's corrosion is yellow, or how reactive it is. In the case of explosive material, it would be how easy it would be to explode, would be the right one. But most of the time, this one's kind of wrong. It would be, most of the time, it would be how much it reacts with things. Like, for example, sodium reacts with water and explodes. It's a metal that if you mix it with water, it'll explode. There are some chemicals where, like nitroglycerin, you take a hammer to it, you drop it, it'll explode. There's things like acid. Acid can eat through metals and containers and catch things on fire. It reacts with everything it comes in contact usually, except for certain types of plastic. So acid reacts a lot, so it'd be highly corrosive. The last one, specific hazards. So they have acid, which is just acid written out. Alkali or base is ALK. Corrosive is COR. Oxidizer, y'all heard about that recent explosion in the Middle East? Beirut, I think it was. They had stored some potassium nitrate, which is an oxidizer used for fertilizer. These things mean it's able to explode, basically. Polymers is with a P, and oxidizer is OXY. It means oxidizer splices on oxygen, and sometimes it's more efficient than oxygen and air, which means a chemical can absorb a lot of oxygen really quickly. Radioactive has the radiation sign. Another important one to look at is the no water. It's a W with a line through it. You should memorize that one. As it means do not mix with the water, or it reacts violently with water. Alright, so looking at the MSDS, usually it begins with the identity number 1, tells you the chemical name, train name, manufacturer of it, address, and emergency numbers. Number 2 tells you the composition or ingredients of it, includes the substance, percent content, a unique number identifying it, classification, and so on. Number 3, hazards. Tells you the dangers for humans and the environment, most important hazards and specific hazards. This is often the number 1 important thing you should always look at. So if you didn't know, acetone, which is very common, is a clear liquid with sweet odor. It's flammable, a serious fire hazard. Very easy to catch on fire. It produces a lot of vapors. Irritates your body tissue, and you should avoid touching it to your body tissue. It is slightly toxic by ingestion. Vapors cause weakness, fatigue, nausea, and headache. Touching it, spilling it on your skin can also cause dermatitis or rash. Next section is first aid. Tells you what to do in case you get on you. Note that you probably shouldn't look at this section after you get in your eyes and you're blinded. Very hard to read a material safety data sheet after you gotten a chemical in your eye. This should be read beforehand. So if you get on your skin, wash with fresh water and mild soap for 15 minutes. If you get in your eye, you need to flush it for 15 minutes. If you inhale a lot of it, you need to go get fresh air. Firefighting, so some chemicals you can't use certain fire extinguishers on. This tells you some information on it about what to do. So one thing is do not put acetone next to any oxidizers, as you can create a bomb. This would be if you accidentally spill it. It's the next section, number 6. If you were to break a large quantity of acetone, it makes the entire area extremely dangerous. Usually what you do is you throw sand in the room, try to soak it up, but mostly you have to evacuate the area and let it all evaporate. Handling and storage, you don't really need to know that, but it tells you how to store it safely. Tells you what, next section, number 8, what personal protection you need to have when using it. It also tells you do not do 750 parts per million within an 8-hour window. And other stuff, exposure, how much you're allowed. Physical and chemical properties.
Nothing, I'm trying not to fall asleep. It's not you, it is.
So section 9 tells you some important physical and chemical properties, like formula weight, formula density. 10, stability and reactivity. So it's considered stable. It also tells you it can make an explosive reaction if it gets next to oxidizing agents. So keep it away from potassium nitrate, ammonium nitrate, and anything else that's considered oxidizer. As if they combine, it forms a explosive. Toxicity. So it is toxic. It destroys your liver and kidneys. Ecological tells you any dangers. So it doesn't say any data yet. Some chemicals you can't put outside because one, it's illegal because of environmental laws. 2, it destroys the environment. Usually acetone evaporates too quickly to really cause any harm, which is why there's no data on it. And how to dispose it. Disposal considerations. You'd have to look up state and local regulations. Transport, you don't really need to know that. It don't be transported in it. But tells you if you want to buy quantities like that. Regulations. If it's regulated, you might need to get a license to store it. And other information. Any questions? Yeah, that's pretty much it. This is just dope.